Okay, guys, can you see the window?
Yes, sir.
Yeah, okay.
Yes, sir.
So, yeah, let's begin. So we had talked about first law, where I had told you that we could put a sign, positive sign here, but then I thought, uh, maybe you guys are accustomed with putting a negative sign with dw. So I think you guys have sort of learned things with dq is du plus dw. All right, so that way we could put it like du is dq minus dw, or um, just in that form. That'll be easy for you. It doesn't really matter, the like the last time I said you, because you need to take a stock of the sign of dw from a system perspective. When the system, whether it's work done by the system or work is done on the system, and based on that you'll have to take a sign of that. So in that sense, it's the dq and dw terms are algebraic sums. It doesn't have to be sign. It is sign agnostic. Uh, the definition would be that the combined changes of the heat and work is what is reflected in the change in internal energy. Excuse me. So that's why I wanted to just correct it a little bit, or to correct in the way that you would find it easy. So next, going forward, of course, we talked about first law of thermodynamics, and then there are a bunch of corollaries that can come out of it. When you talk about an adiabatic process, we haven't spoken about that, but I think it's not something that you already don't know. Um, Adiabatic process is something where heat doesn't go into the system, right? It's like the best example of it. The common example is maybe some kind of a hot beverage or cold beverage in a canister, in a thermos canister, where you sort of no heat is coming out of the system, neither it is going into the system. So that's it's kind of a adiabatic process. So in that process, the internal energy change and work are sort of negative of each other. So if you're increasing the internal energy, then work has to be done on the system, and vice versa. And likewise, if we talk about a cyclic process, and the if system or thermodynamic coordinates transit from a set of coordinates to various other coordinates, eventually end at the same initial coordinates, that will be a cyclic process. And in that cyclic process, the internal change, internal energy change will be zero. Okay, and that's why the term of a state function is coming. It's the properties of a state function is dependent only on the state. The thermodynamic coordinates. If it comes back to the coordinates, it is to be taken that the thermodynamic quantity hasn't changed. Okay. And the mathematical forms of it is what something we're going to read in subsequent slides. So another parametric thing which is very important is to understand the difference between heat and heat capacity. Heat we normally define as the workless transfer of energy. Heat is the workless transfer of energy from one entity to the other entity, whereas heat capacity is the measurement of temperature with the introduction of, or with the transfer of heat into that entity or into that system. That's heat capacity. And mathematically you can write simply as the total heat transacted or transferred, normalized by the change in temperature delta T. dq by dt is the form for heat capacity. And there are two different processes based on which we calculate those heat capacities. First is a constant volume process, which is what people deal with in fluids, typically liquids and gaseous substances. That's generally called the heat capacity at constant volume. And the other one would be the heat capacity at constant pressure. There are functional differences, but if I have to give you a crude or a bulk guideline for things, this CV is something that chemical engineers and mechanical engineers invariably talk about, and that's the constant volume processes that what they are interested in. But you talk about thermodynamics of solids, materials engineers or ceramics guys, physicists who work on constant pressure processes, and they look for changes that happens in a solid, they generally talk about CP. And its functional forms are going to be coming in the next slides. Okay. So if you talk about a constant volume process, then the volume change is zero, and which sort of leads that the work done is zero. There's no work done. And if you go back to the first law of thermodynamics, you see that because this term is coming to zero, the internal energy change is simply the heat transfer. Okay, and that two functional forms is that increase in the internal energy on the system is equal to heat absorbed by the system. Okay, we are putting heat into the system, that is eventually going to raise the internal energy of the system. And conversely, decrease in the internal energy of the system equals to the heat rejected by the system. And the simple example would be that if you are, so see that there is a direct here. Of course, it's not straightforward, but then internal energy is typically related to the temperature. When you say that the increase in the internal energy of the system, that's typically raises the temperature of the system, and here also it is, if you're decreasing it, so temperature eventually is coming down. So from the QV form, you could simply write that CV is then du by dt. That's this U term is related to constant volume process, which is what gives you CV, or du is Cv dt. Simply you can write. Likewise, you have a constant pressure process. And in this constant pressure process, we are defining another heat term, which is called enthalpy. Okay, and it's you said that changes in the energy of an entity when the body is heated at constant pressure isn't exactly internal energy. That has to include the pressure volume of work as well. That quantity is called enthalpy. Okay, and if you write like this, look at the second line here. This is the first law. Delta U is QP minus P delta V. That's the work term, and then you do a little bit of a rearrangement. You would find that U2 plus PV2 minus U1 plus PV1 is the heat transacted at constant pressure, which we define this term U plus PV as the term H, which is enthalpy. So H2 minus H1, that is delta H, and that's the change in enthalpy, and that's the heat transacted, heat transferred at constant pressure process. Okay, and likewise, you calculate CV. CP is dH by dt at constant pressure. So you have CV as du by dt and Cp as dH by dt. And there is a functional relationship between Cp and Cv that I think you are aware of. Cp minus Cv for ideal gases would be considered the gas constant, that's universal gas constant, that's R. Okay, now we need to understand a couple of processes which are reversible in nature and processes which are irreversible in nature. Okay, and in a way you can say that reversible processes are something which are extremely slow processes, and to the point that they are not practical, so to speak. But then there are, of course, have processes which are extremely slow and reversible, and it sort of goes through stages of thermodynamic equilibrium throughout this initial state to the final state. They go by infinitesimally small successive stages, and each stage it would appear that the process is in equilibrium. It's like extremely slow way of controlled way of changing the thermodynamic coordinates, so much so that with little the processes can be reversed, okay, by subtle change in the thermodynamic parameters. On the contrary, irreversible processes are something which are kind of fast, spontaneous, abrupt changes in the thermodynamic coordinates. They don't go in a slow way. They don't go by infinitesimally small displacements or changes in the thermodynamic coordinates. They go by abrupt changes. During the process, they are not in equilibrium, okay, and it'll be difficult for them to be reverted back to the original condition unless aided by external forces, external work. Okay. And it would mean that the work done by these two systems are going to be unequal, and I think in comparing the pressure volume work for a reversible system and irreversible system, we had talked about that in like how reversible work is always larger than the irreversible work. We talked about that in former classes. Okay, but nevertheless, the changes in the internal energy of the system, despite the reversible or the irreversible process, are going to be the same, because the internal energy is a state function. It only depends on the thermodynamic coordinates rather than the processes followed. On the contrary, work done as well as the heat transfer, that would be different for these different processes. So here is an example of a process that on the right which is given. This is a thermodynamic space. I know thermodynamic coordinates with temperature, volume, and internal energy. And let's consider two states, which is given by I and F, and two paths actually depict the movement of the process from I to F through this blue line or aqua line. This is path 1, and this is path 2. All right, the other line. So in a way, for the same destination from the same starting point, two roads are there, and the two processes follow two different roads. And in that process, the at the end of the process, the start and the beginning of the process and the end of the process, if you talk about the states of the system, no matter what the path was, the state of the system is the same, right? In this I and these are the same coordinates as F is the same coordinates, right? So properties which depend on the state are going to be the same, no matter how different paths you've taken. But then properties which do not depend on the state, which depend on the path, are going to be different. Okay, in this process here, the work done is going to be work done in path 1 and work done in path 2 are going to be different. Okay. But the internal energy change of delta U from I to F, followed by the process 1, and internal energy change from I to F, followed by path 2, are going to be the same. That's what is meant by state functions. And there are mathematical definitions to it, and then from the expression of the the thermodynamic function that we're talking about, we can figure out whether it's a path function or a state function, and the relation is like this. So it's something called an exact differential or an inexact differential, right? And it's called perfect differential. Here there is a mistake. If you look at the exact, this is supposed to be inexact. I'll correct that when I make this slide, distribute the slides. So if f is a function of x and y, these are thermodynamic parameters or coordinates, if you call them, and f is a thermodynamic function. Okay, if this is defined by a function of x and y, then you do the mathematical operators like del square f by del x del y is del square f by del y del x. So what does it mean? That means this is what you do: first differentiation with partial differentiation with y, and then you differentiate with x. All right, that means you are doing a change or overall change by doing one change by keeping the other one constant, and doing the second change with keeping the first one first variable constant. Okay, that's what is written, what is meant by this mathematical operation. And this is going to be the same as doing the first partial derivative of x and then doing the second to y. Okay, so no matter in which sequence you do it, despite that the double partial differentiation is not different from each other. If this is the situation, then we call this is mathematically an exact differential, and in thermodynamic terms we call it a state function. On the contrary, if you change things by 1 and then 2, and then in a way you do the change things by 2 and then 1, and you eventually find out these two terms are not same, then this will be called an inexact differential. Here's the mistake. Okay, this is an inexact differential, and therefore this thermodynamic function f is going to be a path function. Right, it's as simple as that. We can give any thermodynamic function to you, and then its variables and its dependence that can be given, and then you should be able to calculate whether that's a state function or path function. We have done an example. We can go with that. So if you take an example of, say, W is work. All right. So first we need to do is we need to find an expression for dW, okay, in terms of the variables that we have, P, V, or T. Those are the common variables. So if you take the universal gas law, is PV is RT, we're not using N here, that would give you that PdV plus VdP is RdT. You know that R is a constant. And since PdV is something which can be expressed as dW, then dW becomes RdT minus VdP. All right, and you simply divide by, you reorganize V as RT by P. You have the term RdT minus RT by P dP, or RT dP by P. All right, now this becomes our functional dependence of this term dW with the variables which is T and P is pressure. All right, now what we need to do is we need to do this, find whether the function is an exact differential or an inexact differential by doing partial derivatives, by taking partial derivatives here, and that is from this expression dW is RdT minus RT dP by P. You take a first derivative with temperature, this del W by del T at constant pressure, which is giving you R. And then you, for this quantity, you take another derivative with regards to P, because you'd kept P as constant here. Now you're going to change P here. Now del square W by del P del T, which is giving you because it's a constant, the differentiation is going to be 0. On the contrary, let's first change the variable P here, and then in a different approach, what you do is del W by del P. You're now changing the variable P and then trying to find out what's the change in W, which is giving you the term minus RT by P. And now here temperature was kept constant, and then you do the double derivative by changing it with temperature, which is del square W by del T del P, which is giving quantity RT by minus P square by taking the derivative of minus 1 by P. So in this process, in this method, what you find is del square W by del P del T is 0. Here del square W by del T del P is some quantity, it's RT by P square. And these two quantities are not the same. This is not the same. Yeah, of course, this is not the same is equal to RT by P square. So that means this function is not an exact differential. Okay, it is an inexact differential, and that's why it cannot be a state function. No, it's a path function. So work is a path function. Now let's see if we change the function dw slightly differently. Let's think about a function which is dw by t. This is, I don't know if there is a particular term for this function, but then let's define a function. Let's do it mathematically. We call a quantity some d phi, okay, which is equal to say dw by t. We're just taking some number and the next. We are just telling a functional dependence which is slightly different than work. All right, just say dw by t. And likewise, you should be able to calculate what is that quantity d phi, because we had an expression for dw. Now you normalize it with temperature. Now you get an expression like r dt by t minus r dp by p. That's functional dependence of this particular function. Okay, and then we need to test whether this is an exact differential or not by doing the same process. You take d phi by dt, del phi by del t at constant pressure, which gives you r by t, and then you do del square phi by del p by del t, because here pressure was constant. Then you need to change in the second step with the change in pressure, that gives you a term 0. Likewise, you do the first partial derivative of phi with regards to p, that gives you a term minus r by p. And now in the second stage, you do the partial derivative with regards to t of this whole term, as del square phi by del t del p, which again is giving you 0. And you see that no matter how you do the double differentiation, both the terms are giving you 0. That means these two are equal. That means this function dw by t is an exact differential, and therefore it will be called a state function. Means it only depends on the initial and final thermodynamic coordinates, but not the way it has gone about. It doesn't really matter what path it follows. So that's state function. And internal energy and enthalpy are typical examples of state functions, and work done and heat transfer are not state functions. They are path dependent.
Sir,
Yeah.
sir, sorry to interrupt you, but in the previous slide, सर जो दूसरा वाला हम लोग सेकंड ऑर्डर डेरिवेटिव कर रहे थे हम लोग उसमें शायद सर थोड़ा सा मिस्टेक है आई गेस
मिस्टेक है या टेल मी क्या
सर कैन वी गो बैक टू द प्रीवियस स्लाइड प्लीज
या दैट्स द प्रीवियस स्लाइड वी हैव इट हियर
सर व्हेन वी डिफरेंशिएट with respect to delta p it is minus RT by P, and when we are doing the second order differential which is with respect to temperature, isn't it supposed to be minus R by P?
Minus, oh yeah, I think there is a mistake. Now we need to change, we need to do with temperature, isn't it?
Yes sir.
Yeah, there's a mistake. So I did it, I first do it and then put it onto the slides, so there was a mistake that has gone about. Yeah, thanks for pointing it out. Of course, we need to change, we need to do it with regards to T, isn't it? Yeah, yes. So P would remain and then, yeah, got it. Yeah, we'll change it.
Yes, sir.
Glad that you pointed it out. Okay. Yeah, but anyway, it doesn't really change the final thing, isn't it? It's
Yes,
the
sir.
same in the sense that both these two terms are unequal, and therefore that it's a path function. Yeah, thanks for pointing out. So yeah, please don't please look at these slides and the signs or the things that are written here, because these are not my handwritten ones. I write it by hand and then I convert it to the slides, and writing all those differentials and big functions in a LaTeX form. I don't know, you guys are aware with LaTeX writing, because these those are very good for mathematical equations writing and all. But the problem is you'll have to write codes to be able to write, let's say, a thing like this. And it's very easy to actually type something else from the note that you sort of follow. So there could be little mistakes. So don't go by these numbers or these things that is written here as gospels. You need to always cross check with using your mind, and then by comparing it with books and all that. That's the problem with these mathematical things, because when you do it on the board, you are in the game and then you're doing it by yourself. But then it has come to a point that I do it on my notes or something, and then I convert it to the slides. So there could be mistakes, silly mistakes, no major mistakes, but then silly mistakes can be there, and you got to be mindful of that, right? Okay. So I think this one is what we had talked about. I think I'm coming back to some of the slides, and this is where we talk about the work done in a reversible process, where you take care of the all shaded area. On the contrary, when we talk about in an irreversible process, we just talk about the work within this area. That's uh, that's what is smaller. The work done is smaller in an irreversible process as compared to the reversible one. Okay. Likewise, some of these expressions are there where you can find out functional relationship with um, the other thermodynamic variables. Um, and this is that there are many ways of deriving the term of pressure volume relationship in an adiabatic process, and this is one such. You can have different ways of doing it. It's as simple as that. It's dq. This term delta, this delta we write sometimes so as to tell that it's not an exact differential. Okay, in that sense, this also should have been written del w rather than dw. Okay, so don't mind about that, and I don't even mind if you write dq instead of delta q. Just to I have included this one just to point out that in some of the books you'd find some of these inexact differentials to be written in the form of delta or d with a bar, but it just tells you that it's not an exact differentials. Other than that, it's the same. So from this you can get expressions of Cv dt and Cp dt. I think you guys understand that. So CvDT is minus PdV and CpDT is minus VdP, and then this term that Cp minus Cv is R is something you can prove by yourself, but then that'll be long enough. We will skip that. And there's a ratio of this Cp by Cv, which is gamma, right? And since Cp is this R is a positive quantity, so Cp by Cv is always going to be more than 1. And you guys know that gamma can vary depending on the kind of material that you're talking about. Talk about monoatomic gas is something, diatomic gas is something, and then likewise, it depends on the degrees of freedom and things like that. And likewise, it will be changed in the Cp and Cv, and then correspondingly, the changes between the internal energy and enthalpy are going to be that much different depending on the values of gamma. All right. So if you talk about Cp by Cv, then you can talk about V dP minus P dV. That's the number you can get from these. All right. And that's gamma. If you reorganize this is gamma dV by V is minus dP by P, and by doing a process you can get the term PV to the gamma is constant, right? So in an adiabatic process, PV to the gamma is constant, whereas in normal sort of universal gas law, is PV is constant, is what we ordinarily take. And likewise, you can get functional dependencies of dependence between T and P and then T and V, much from this function, or you can do again the same process and then arrive at this expression, which tells you that TV to the gamma minus 1 is constant, and T gamma, P to the 1 minus gamma is also constant. So these are the functional relationships between the thermodynamic variables Tp and V in an adiabatic process, and we can actually have a host of small numericals that you can solve just to familiarize yourself with these quantities and the formula. But that we'll have it in terms of some assignment or some quiz in due course. I think some of these things are you already have done, is simply numerical kind of thing. But there's one interesting thing that I would like to point out is that are you guys aware of this PV diagram? Right, this is exactly what we drew here. It's a pressure and then the volume, and then you draw some diagrams and all that. And let's say if this is a diagram, and let's say it's an isotherm, we're doing it at constant temperature, then that will be called an isothermal process. And when you talk about a process which is carried out with constant volume, okay, which is what do you call that? Isochoric process. Then the like the red line here, the isochoric process is something which will be like a simple straight line here, because this is what the volume coordinate is, and then if volume doesn't change, then the process the process is going to be constant here. It's going to be a simple vertical line for an isochoric process. Likewise, you talk about an isobaric process or isobar, then bar relates to pressure, and the pressure is going to be constant, and in that sense, that process, an isobaric process, is going to be a simple horizontal line here. This is isobar, this is isochore, this is isotherm. All right, and there is another process which is called an adiabat. Okay. Some people call it adiabatic. No, adiabatic is not. The term is adiabat. That doesn't mean that it's something which is not diabetic. Processes are not diabetic. People are. Humans are diabetic. Processes are not. But anyway, jokes apart, that is called adiabatic process. Right? In the adiabatic process, how do you do that? This is an isotherm. How is going to be the adiabat? That's a question you got to think about, and that's a new thing in the sense that you need to look at the slope. If you look at the slope of this PV diagram, what's the slope? Slope is dy by dx, isn't it? That's the y-axis, and that's the x-axis. You typically define slope as dy by dx. Okay. How this one changes with regards to this for any of these processes. If you look at that, then the slope would be dp by dv. This is what we've tried to figure out here. All right. If you talk about the dp by dv in adiabatic process, then you end up with the term minus gamma p by v. All right. It's minus gamma p by v. On the other hand, if you talk about the dp by dv, that is to try to find out the slope in an isothermal process, that's simply minus p by v. Right, so this is what we're seeing here. If you talk about this is an isothermal process, and then you figure out the slope here, that's actually p by v, minus p by v. Of course, that's a minus sign because it's a negative slope. All right, but if you talk about the slope of an adiabatic process, then you get minus gamma p by v. There's an additional term, gamma here. All right, because since gamma is more than 1, okay, the slope is going to be steeper. That means it's a steeper negative slope, which is going to be written here as a steeper negative slope. So it's got to be something like this. All right. If you started from here, it's going to be something like this. It starts from here, it's going to be something like this. So there's a marked difference in the slope between the isothermal process and then adiabatic process, and that's how you can figure out whether it's a isothermal or adiabat. All right, and much of these we can do in subsequent classes. So okay, so we come to so the basic ideas of work and the processes, and then going back to the earlier ideas that we had spoken about, that in the first law of thermodynamics we can actually add, instead of pressure volume work, other works which typically concern the material scientist or the physicist, which are not related to pressure volume work. Okay, so there's a host of things that we discussed. It's the other day I told you to think about work in terms of force displacement kind of generic quantities. Okay, in a very sort of loose terms, we can say that the cause effect way, or some people also define it, there's a change in something against the resisting force, against the force which sort of resists the change. That's what I call it, the cause and effect kind of thing. So force displacement, cause effect, or the change versus the resistance to change, that conjugate systems would give you a host of different kinds of work, which is what is written here. There's a work done in the extension of a wire, dW, this is FDL, and then of course the surface of films, gamma dA, that's the work done here. Work done in moving a charge is VI dt, that's the power term, and multiplied by the time part, and of course in polarizing a dielectric solid, EdP, and then magnetizing a paramagnetic solid, which is mu 0 HDM. So these are the different kinds of forces we can take in place of the pressure volume work and apply the first law of thermodynamics there. So before closing, I would like you to think about this. Of course, some pictures are taken from, these are the books, the thermodynamics materials books from David Gaskell. This is not where I've taken some figures from here, but then I generally follow this, and then I asked you to also follow this one. Heat and Thermodynamics, that's a wonderful book by Zemansky and Dittman, as I told you. And most of the figures that I've taken, it's by the Atkins Physical Chemistry, is a world famous book by Professor Peter Atkins of Oxford University. Right. So with this, I close and ask you a question, in the sense that if I take, let's say, a very big glass slab, all right, and take it to a height, and then I drop it down. All right, that's the process. I take it to a big glass plate, and then I drop it down. Okay, how do I apply the first law of thermodynamics to this one? You think about it, and then we'll talk later. Let me close this today's program, and then we can go for some discussions. Right? Okay.